So still in chapter 5, talking about polynomial and rational functions. And the next two sections are going to talk about zeros of polynomial functions. So we first start by talking about real zeros, and then we're going to talk about all kinds of zeros. So the first objective is going to be to use the remainder and factor theorems. So we're going to talk about some theorems and learn how to use them. Then I'm not going to talk about Descartes' rule of signs because I don't find it that useful. You can read about it in the book if you like. And then we're going to use the rational zeros theorem to list the potential or possible rational zeros of a polynomial function. Number 4 is going to be find the real zeros of a polynomial function. And then solve polynomial equations. Okay, and then again, the theorem for bounds on zeros and the intermediate value theorem. You learned the intermediate value theorem in calculus, so I know you'll see it there. And I don't find the theorem for bounds on zeros that useful. So I'm not going to take the time to go over them, but you can read about them in the book if you like. So I want you to recall these 4 equivalent statements, and it would be a great idea for you to write them over and over again until they're just part of what you know. So if the number r is a real zero of a polynomial function, then we also know that the point r0 is a point on the graph of the function, and the r is an x-intercept of the graph of f. We also know then that x minus r is a factor of f, and being a factor means that you divide evenly into. So if 6 times 7 equals 42, it means 6 is a factor of 42, which also means 6 divides evenly into 42, and divides evenly means there is no remainder. So you already know a lot of this language as it applies to numbers, and now we're just going to apply that same language to algebraic quantities. So if we're dividing one polynomial by another, we need some language. The dividend is what you're going to divide into. So this is the negative 4x cubed plus 5x squared plus 8. You're dividing it by x plus 3. The OR ending means the one that's doing something, the divisor. X plus 3 is dividing into the dividend. Then the quotient is what you get if you do the division problem and it's what's on top. In this particular example, you're missing 0x, so you need to put a placeholder. There's no x term, but we need something in every degree spot. So we put 0x in there to be a placeholder, but there aren't any x's there really. So we're going to have negative 4x squared up here. Then this times this goes here. And subtract. And remember, subtract means add the opposite. So I'm going to have 17x squared plus 0x plus 8. So then I'm going to have plus 17x. Multiply, I'm going to get 17x squared plus 51x. These came down from above. And I'm going to subtract, which means change all the signs and add. So I have negative 51x plus 8. So I'm going to have minus 51. So I'm going to have minus 51x minus 153, and I'm going to subtract, which means change all the signs and add. So it looks like I have a remainder of 161. So 161 is the remainder. The quotient is the part on top, minus 4x squared plus 17x minus 51. And you can check polynomial division by doing the quotient, negative 4x squared plus 17x minus 51, times the divisor, x plus 3, plus the remainder, and make sure it equals the dividend. So let's do the distribution. I'll have negative 4x cubed plus 17x squared minus 51x minus 12x squared plus 51x. These numbers should be really familiar. Minus 153 plus 161. So I get negative 4x cubed plus 5x squared plus 8. Check. So we know for sure we got the right answer, and the way we write it is, here's the answer. Negative 4x squared plus 17x minus 51 plus 161 over x plus 3. So here's the remainder, and here's the divisor, here's the quotient. Okay, so what we just did is called the division algorithm for polynomials, and this just formalizes that result. So if f and g are polynomial functions, and g is a polynomial with degree greater than 0, then when you divide, you get a quotient plus a remainder over the same as the original divisor. So if you multiply both sides of this by g of x, do you see that then you get that f of x equals, distributing, q of x times g of x plus r of x. So r of x is either the 0 polynomial, which means g divides evenly. Remember, if you get no remainder, it means you divide evenly. Or the remainder is a polynomial of degree less than that of the divisor. So you keep going until the remainder has a degree smaller than the degree of the divisor. Okay, so let's talk about the remainder theorem. This is pretty cool. So if f is a polynomial function, so this only works for polynomial functions, if f of x is divided by x minus c, then the remainder is f of c. And there's a little proof of this, but Math 12 students don't usually want to see the proofs, but it is in your book. And I can show it to you if you come to my office and you'd like to see it. So remember synthetic division, and if you don't, jump back to page 58 to 61 to remind yourself. Okay, and this example says, use the remainder theorem to find the remainder when f of x is divided by x minus c. So here's the f of x, and you're dividing by x minus 2. So remember, when you're doing synthetic division, the number that you put in the little pocket here is the c of the x minus c. So 2 is what goes in the little synthetic division pocket. And then you have 4 for the x cubed term. You have to remember to put 0. Sorry, this is for the x to the 4th term. You have to remember to put 0 for the x cubed term. Negative 15 for the x squared term. You have to remember to put 0 for the x term, and then negative 4 for the constant. Okay, synthetic division says drop down the first term. Then do 2 times the 4 is 8, and add. 2 times the 8 is 16, and add. 2 times the 1 is 2, and add. 2 times the 2 is 4, and add. So this is the remainder. So that means x minus 2 divides evenly into f of x because the remainder is 0. And that also means that f of 2 equals 0. So this 2 here you put it here, it says the remainder is the result you get. So you could put f of 2 in here and go 4 times 2 to the 4th minus 15 times 2 squared minus 4. And it is 0, but boy, that seems like a lot more work to me than doing the synthetic division. So a more typical type of question I would ask is to use the remainder theorem to find f of 2 for the polynomial above. And then I would expect the answer to look like f of 2 equals 0. So let's do it if it said, what if it said use the remainder theorem to find f of negative 3. Well, that means you would put negative 3 in the little pocket, and you'd have 4, 0, negative 15, 0, negative 4. Bring the 4 down, multiply, negative 12, add. Multiply, 36, add, get 21. Multiply, get negative 63, add, get negative 63. Multiply, get 189. And add to get 185. So this was a pretty quick way of seeing that f of negative 3 equals 185. Then you could double check it by actually plugging in, but I think synthetic division's a lot faster. So that's my strong preference. Okay, so now let's talk about the factor theorem, which actually has two parts. First, it says if f of c is 0, then x minus c is a factor of f of x. And then it goes back the other way and it says if x minus c is a factor of x, then f of c equals 0. Okay, so for that same problem, let's use the factor theorem to determine whether x minus c is a factor of f of x. So we did the synthetic division with 2 here. Make sure you're clear that it's 2 and not negative 2. And we got a 0 for the remainder. So this says if f of c is 0, x minus 2 is a factor of f of x because we got a 0 remainder. And let me just mention that this other part that's left here represents the other factor. So this is the constant, this is the x term, the x squared term, and the x cubed term. So it says x minus 2, the factor. The other factor is 4x cubed plus 8x squared plus x plus 2. So you could check by multiplying back together that that should equal f of x. So a polynomial function cannot have more real zeros than its degree. So that helps give you an upper limit on how many zeros am I looking for. So whatever the degree is, that's the maximum number of zeros. And remember that we count multiplicity. So if we have x minus 2 cubed times x plus 3 squared times x minus 1, we would say 2 is a 0 of multiplicity 3. Negative 3 is a 0 of multiplicity 2. And 1 is a 0 of multiplicity 1. So we have degree 6. So we count the multiplicities. Okay, so here's the rational zeros theorem, and I'm going to start here on a second part of the movie because this topic's a little bit long.